In this talk, we look at what it means by limit of a function. So limit of functions usually described by this writing. So what does that mean? So it reads as the limit of function f of x as the input variable x approaches a given value c. So c is given, f is given. All right. So right now, I want to emphasize the most important ingredients you should never forget when you write limits of a function. So the whole thing looks like this. And you should always contain this because f tells you what you are looking at. X approaches c tells you where you are looking at. So whenever we are talking about a limited function, that is a very vague idea. If you want to do evaluation, you always have to have the information limit of what the function at which point, okay, as x approaches c. Okay, so when you start solving more and more complicated problems, you might start getting lazy, and you start writing like limit of x approaches 0, and you like knew which f you're talking about, and then just get lazy and say, the limit equals 1. So this is not good because the what is missing. Or you could be like, I know like which value x is approaches to, so you say like the limit of the function equals 1. This is no good either because you are missing the where component. Okay, so this is very important when you solve a problem. When you're talking about limited function, you must always include the where and the what. Don't get lazy. Let's look at this example. I have a function f defined as a piecewise function. Okay, I know this looks a little complicated, but remember, we are patient. We are good at math, and you are patient. So don't just freak out yet. Just keep reading. Then we have a given relation between the input variables and output variable. I'm not writing the y out, but the value f of x refers to the output value. Then we are looking for the limit of this function when x approaches -1. Limit of same function when x approaches 0. Limit of same function when x approaches 3. So we're gonna use this example to see how we find limit of a function. Okay. So before we go ahead do evaluations, I wanna sketch the graph because this will help us to see the concept. XY plane. So remember, when I have a piecewise defined function, I look at piece by piece. Okay. So on this line, I have the x value. So on the left hand side, the y-axis, that's where x is negative. So I know when x is negative, the output value y is just all ones. Okay. And I want to give a big empty circle here because this line only talks about the situation where x is negative, okay, less than 0. When x is equal to 0 is something else. I have to read the second line. So the second line tells me that when x equals 0, okay, so when x is right here, what is the upper value? The upper value is 2, so let's go 1 unit up to the big fat dot here, so that's 2, okay? And when x is greater than 0 but smaller than 3, less than 3, so let's see, so going from here to 3, so let's do 1, 2, 3, 3's here. When x is between 0 and 3, not including 0, not including 3, I again have output value to be just the 1, so it's the same height. And when we get to 3, I again put a empty circle to emphasize when x equals to 3, I don't know what value it is yet. And then let's read the last piece. When x is greater than or equal to 3, the output value is 0. Okay, so when x equals 3, which is what is the situation? It's here, right? So 3 satisfies these conditions belong the range greater than or equal to 3. So my corresponding output value is 0, and it's all 0 all the way to the right of 3, like that. Okay, so what you see here is the graph of the given function f. Then let's now look at how we find limit of function and what it actually means. So the first one is to find the limit of f when x approaches minus 1. So let's see, this is where the minus 1 is. Okay, so x approaches minus 1 means you have to take care of the situation when x approaches 1 from the left hand side and when x approaches minus 1 from the right hand side. So this is the so-called two-sided limit. Okay, so we have to take care of the situation when x goes from the left hand side and when x goes from the right hand side of minus 1. Okay, so by looking in the graph, you can see that when x is equal to minus 2, the f of x is here. When x equals, let's say, minus 1.5, the y value is still here, and just keep approaching minus 1. Okay, so you see, like, the y value stays put. It still stays 1. The value does not change. Let's look at the other side. So I don't care what happens over here because they are very far away from minus 1. Eventually, what I only care about is when x value is very close to minus 1, okay? So I don't care the part that's far. I only care about like the neighborhood of minus 1. So when x is over here, the y value is 1. When x is over here, it's still 1. Over here, it's still 1. So you can see like the value of the f of x stays 1. So both the left hand side and right hand side, they both give me 1. So I have the first limit equals 1. Okay, let's go to the second example. Second example, I am looking at the situation x approaches 0. Okay, so now I have the f. I have the new where. The new where is 0. Okay. So this time I wanna see what happens when x approaches 0. Okay. So let's start from the neighbor from the left hand side of 0. So that's here, right? So you can see that on the left hand side of 0, all the output value is 1. So 1 here, doesn't matter how close you are, it still stays 1. Similarly, on the right hand side, I have the output value 1, output value 1, so I just keep traveling. Okay? So you can see that if I travel along this course, think about your driving, okay? Think about your driving. If you travel along this course, you're gonna bump into like this value, which is 1, even though it's this empty circle there, okay? So in this case, we still have the limit equals 1. The left hand side approaches 1 because all the output value of x gives me 1. So as long as I have x approaching 0, I get 1 from the left. And as long as I have x approaching 0 from the right, I get 1. Okay? So here is a good example that tells you the limit of f when x approaches c is about the function value, the neighbors of c. It's not about f at x equal to c. Okay? So here when x equals 0, the function value is equal to 2. But what we care about is the function value of the neighbors of 0. So what are the neighbors of 0 is this guys. They are the neighbors of 0. This guys, they are the neighbors of 0. And all of their associated function values are 1. Okay, so I do not care about the function value at the c, meaning the 0 in this case. I do not care about the function. It's about the function values at the neighbors of c, both the left hand side of c and the right hand side of c. Okay, so this is very important. It's all about the neighbors, not about the c itself. Okay, so this is important. Let's move on to case number 3. Limit of f when x approaches 3. Okay, so when x approaches 3, here's our 3, x equal to 3. So remember, I'm not looking at what happens when x equals 3. I'm looking at what happens when x is approaching 3 from both sides. So let's see. For the neighbors on the left hand side 3, what do you have? What function values do you get? You get 1. So because they're here, right? So they approach 1. When x approaches 0 from the left hand side of the 3. So in this case, I can say the limit of f where x approaches 3 from the left. Okay, so the minus sign meaning it's less than 3. Okay, so it's left hand side of the 3. By the graph, I can tell that it gives me 1 because we're over here, right? However, if I look at the right hand side, when x approaches 3 from the right, I'm gonna use plus sign, meaning it's like very close to 3 but more than 3. So we're looking at these neighbors. Okay, so when x equals 3.1, we have 0. When x equals 3.01, we have 0, because that's what this definition tells us. Okay, so you can see that for all the x values that are greater than 3, the output values are just 0. Okay, so now what do you see? You see that when you have x approaching 3 from the left, you see the value 1. When x approaches 3 from the right, you see value 0. So they do not match. The limit from the left hand side and the limit from the right hand side, they do not match. One side gives you 1, the other side gives you another value, that's 0. So in this case, we actually say this limit does not exist. And usually we'll just write D and E to refer to the limit does not exist. Okay? So these guys are called one-sided limits, and the most common ones are two-sided limits, and because they are the common use limits, so we usually just call them limits. So whenever we talk about limits without the plus or minus sign, we're talking about two-sided limits, and the limit exists only when both the left hand side and the right hand side give you the same value. Okay, so we have one case where the behavior of the left hand side and behavior of the right hand side, they do not match. In this case, we say the two-sided limit, when x approaches 3, it does not exist. And number 2, even though f of 0 equals 2, but remember, limit is not about f of 0, the limit is about f of x when x is close, very close to 0. So still we're looking at the values where x are close to the neighbors of 0. So from the graph, we can see the left-hand side gives you 1, the right-hand side gives you 1. Therefore, they match, and we say the limit equals 1. And the last case, which is our first case, is when x approaches -1, and we can see that in this case, the limit also equals the function value, meaning this also equals f of -1. Why? Because you can read when x equals -1, which category does it fall into? It's this one, because -1 is less than 0. So when input value is less than 0, your output value is 1. So you can see that the limit, now the behavior of the neighbors of -1 equals the behavior of x equal to -1. Okay? So that's the very basic and rough idea about limits. So let's recap. When we talk about the limit of a function as x approaches c, we write it this way. So when you see this sentence, you know we're talking about this notation. When you see this notation, you should know we are talking about the limit of f as x approaches c. Okay, so this is notation, this is writing out in English. And when we compute, or when we try to write the limit of function, we must always include the two ingredients, that is what and the where. Okay, and even though I say where, but I actually just mean like when x is approaching c. So we're not looking at the f of c, we're looking at the values, function values of neighbors of c. Okay, so function values of the neighbors of c. Okay, the behavior around the c, not the behavior at c. Okay, so I hope this is clear. So this is important. Don't drop the where, don't drop the what when you are dealing with a limited function.